Okay, hello everyone. Welcome to another episode of Science and Technology Q&A for kids and others. So I seem to always not get finished with all the questions that come in a particular week. So there's always a supply of them to start off with, and today is no exception. So let's see, the first question I have here is from a Dharma asking about my thoughts about Claude Shannon, information theory, information entropy, and so on, and commenting on what do I think about its significance and the story of it. Unfortunately, I never met Claude Shannon. Claude Shannon did his most well-known work in information theory in the 1940s and early 1950s. And actually, although he worked at MIT and lived quite close to where I live, he had sort of become something of a recluse even by the 1960s, and had a lot of exotic hobbies and a lot of wonderful pieces of kind of hacky development of computer-like things, whether it was computers to beat roulette, where you would measure off the timing of a roulette wheel by clicking something in your shoe, or all kinds of other schemes for beating the stock market, and all kinds of other things like that. But his best known work was work on information theory. What is the idea of information theory? The question is, in a sense, if you have a message, how much true information is there in that message? How much is there a way to measure the sort of information content of a message? The message has something to say. It might tell you that your pet dog has just won a dog competition or whatever it is. But if you just ignore the meaning of the message, you just say, how much information content is there in this message? Well, today we're pretty familiar with one measure of that. It's like, how big is the file that contains the text that is that message? And in that file, in a first approximation, every character of the message takes up 1 byte. That's not quite completely true, because it's true in English, where we have only 26 letters in our alphabet. But if you go to an ideographic language like Chinese or something, Japanese, you'll have 30 to 50,000 different signs that each represent a word or a piece of a word. And so they're not quite, it's not the case that you can specify every one of those in just a single byte. And typically those are specified using this Unicode standard these days, in which those languages fit into 2 bytes. Each character, each sign in those languages fits into 2 bytes. So what is a byte? A byte is 8 bits of information. Each bit is a 1 or a 0. And so in 8 bits, if you have them all independently chosen 1 or 0, there are 256 possible configurations of that, from 00000 8 times to 11111 8 times. The total number of different possibilities is 256. So you get to encode 256 different possible characters in that 1 byte. When you have 2 bytes, you get the square of that number. So you get to encode 65,536 different possible characters. And most of the current glyphs of the world fit in that number of possible characters. There's been a big sort of escape of characters, which is emoji. People generate all kinds of emoji, and as you generate thousands and thousands of emoji, you no longer have them be able to fit in the 65,000 possible sort of slots there. And so there are now additional like 4-byte versions of Unicode, which allow up to 4 billion characters, which should be enough emoji to supply the world for a long time. And also some of the more obscure and ancient languages, like Babylonian cuneiform or something like this, those fit in beyond the so-called plain zero Unicode. In any case, so basically you have a message, and the most obvious way that you can send the message is to, let's say, put it in a file, or you could take your file, you could send it by email, you could send it through a text message or something like this. But basically, every character in the file is, if it's in English, represented by 1 byte of data, which corresponds to 8 bits, which is 256 possibilities. And there's sort of a convention that that characters in English get represented by particular numerical codes, numerical bit patterns in this byte. It's the ASCII convention from the 1950s, I guess. I always forget this. I think capital A is, I think, 65 for whatever reason. And capital B is 66, if I'm right about the 65, and so on, just follows through the alphabet. But each letter of the alphabet is assigned, in uppercase and lowercase, is assigned a particular numerical code, and that's what that's how the individual letters in the message are represented. Okay, so in a first approximation, if I make a message and that message is 1,000 characters long, 1,000 letters and spaces and so on long, then I'm going to use 1,000 bytes to transmit that message. Okay, here's a key observation. You're sort of wasting effort to send every letter separately. Here's why. Let's say you have a letter Q in English. Then with overwhelming probability, that will be followed by a letter U. So you don't really need to, if you had the right sort of thing, most times you send a Q, you don't need to bother to send that U after it. And in general, there are lots of these kind of pieces of sort of redundancy in English, places where you can kind of predict what's going to happen based on what you've already seen, and at least with a good chance you can predict what's going to happen. Okay, so how do you use that? Well, the most basic thing is that in English, different letters occur with different frequencies in a typical piece of English text. So E is the most common, T is next most common, not sure what's most common after that, but it goes on. And then on the least common end are things like Z and Y and X and V and so on. And so, okay, so given that, what is the best way to send a message? Given you're going to be sending a lot more E's than Z's, what does that mean about how you send a message? Well, this was already thought about back in the 1800s and the 1830s, I think, when Samuel Morse was using telegraphs to send messages. And what is a telegraph for people in the younger end here? It's before my time actually too, but before there were telephones. So, you know, telephones allow you to turn your voice into an electrical signal, transmit it to wherever it's being transmitted to, and get back voice at the other end. Before that was possible, you could at least send little bips by through electrical wires. And so you would have this device where you just have a little key, and you press the key, and every time you press the key, it makes an electrical connection, and that causes the voltage to be a little piece of current to be sent down this wire, and you could send it, and people laid telegraph wires all over the country, all over the world, as a way to communicate information. And so on a telegraph, how would you send a message? Well, what you would do is you would have two kinds of things. You could make a dot or a dash. A dot would be a short bip, and a dash would be a longer bzp, depending on how long you held down this telegraph key. So you're turning whatever message you're going to produce into a bunch of dot, dot, dots, dash, dash, dot, dash, dot, et cetera, et cetera, et cetera. And so that was kind of the approach to sending messages. And then the question was, what was the best way, given that you were going to be sending a particular piece of text that way, what was the best way to encode it so that you had to put in the least effort clicking on your telegraph key? So what Samuel Morse realized is that if E is a shorter code than Z, then on average, the amount of effort you have to go through to send a message is going to be less. So he made E be a dot, T be a dash. And I have to say, I'm sorry to say, I don't know Morse code. I know a few other letters, like S is dot, 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 O is dash, 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 I know that because the famous sort of distress signal SOS is ... dash 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 ... So, but in any case, with Samuel Morse's scheme, you took a piece of text, the E's were short, the Z's were much more to send. And if every letter had been an equal length to send, then you got 1,000 characters. Let's say each letter was represented by 4 different elements in this telegraph thing, then you would have 4,000 times you have to press the key. On the other hand, if you use Morse code, then you have much less than 4,000 key presses, because you've got lots of E's which are just one element, and the Z's might be 5 elements, but they're much rarer. Okay, so this idea of make the common stuff be encoded with something shorter is a general way to make what you have to send in a message shorter. So what Claude Shannon got to thinking about was, what's a general way of thinking about how short can you make a message? What's a general way of understanding how does this Morse code thing, which we have one particular example of there, what's a general way of what's the best what's the sort of approach to making Morse code that will work for everything? And what he realized was that there's a sort of way to think about that mathematically that actually is very similar to the way one thinks about questions about in physics, about thermodynamics, about the question of if you have this gas, it has all these molecules bouncing around in certain ways, but you only need to know some features of it. How many different underlying configurations of the gas can there be? Anyway, the mathematics of that question turns out to be the same as the mathematics of the question that Claude Shannon was interested in asking. And the big result is P log P. So the idea is for every, okay, so here's a way to think about it. And this is a little bit mathy, but bear with me for a second. So let's say we've got a bunch of binary bits, ones or zeros, that we're going to use to represent something. Let's say we have 4 possibilities that we're trying to represent. Well, then we need 2 bits to do that, because with the 2 bits, we can have 0, 0, 0, 1, 1, 0, 1, 1. That's 4 possibilities. So if we're trying to represent 4 possibilities, we can do that by just using 2 bits. Okay? If we're trying to represent, let's say we're trying to represent 7 possibilities. How many bits do we need? Well, 2 isn't going to be enough. 3 bits, we can deal with 8 possibilities. That's 2 times 2 times 2, 2 cubed, or 8 possibilities. And in general, if we have n bits, we can deal with each bit doubles the number of possibilities we can deal with. So it's 2 times 2 times 2 times 2 n times, or 2 to the n. And so that means, for example, if we have 8 bits, that's 2 to the 8, and 2 to the 8 is 256. And that's the thing I already mentioned, is the number of possible configurations, the number of possibilities that can be represented by 1 byte. Okay, so what Shannon noticed is if you have all these different possibilities, then you can, if you have, let's say you have, I don't know, S possibilities, then the number of, what you need to know is what power of 2 gives you gives you S, basically. And that's the logarithm to the base 2 of S. That's the mathematical representation of that. And so then the question is, if you were looking at all these different possibilities and each of them occurred with equal frequency. So let's say there were 8 possibilities and each of them occurred 1/8 of the time, okay? Then what you could do is you say, you just say, what are the probabilities with which these different things occur? Okay, there are 8 possibilities, each 1/8 of the time. The log of that probability, that log of that 1/8 is mathily minus the log of 8, or otherwise known as log to the base 2 of 8 is 3. So that would be minus 3. So in other words, if you look at the probability, if everything was equally probable, then the probabilities would be 1 over the number of possibilities, and the log of that is basically minus the exponent of the number of possibilities. So it kind of works out the same way. Okay. Now the question is, if different ones of these different things that you might transmit, different symbols you might transmit, occur with different frequency, how do those contribute to the total number of elements you on average need to send? So in the Morse code case, because E is the most common, it has a high probability. Z is less probable, but you code them, you can send them as different lengths. Anyway, the end result is that the thing that tells you what the expected length, what the best possible length that you could achieve by encoding all these characters in the optimal way, is this sum of p log p for each probability p of the different possible symbols. And the way that works is, first thing you do is you say, okay, E is the most common, Z is the least common. That's looking at single letter frequencies. Then you can go on and look at digrams, 2-letter pairs. For example, TH is pretty common. ZQ is extremely uncommon. Probably, if you looked on the web, the number of places ZQ occurs in the whole many terabytes of data on the web, of textual data on the web, is really low. So TH is really common. You should encode that with something really short. ZQ is really short, really uncommon. So you can encode that with something incredibly long. It's not going to matter for the length of the message. So the question then is, what is the amount of reduction you can get if you coded things in the best possible way? If you found the best possible way to represent TH with a short thing, ZQ with a long thing, and so on, how short can you make a message in English? Okay, so Shannon's formula basically tells one the answer to that, and it tells one that for English, the answer is about half. So in other words, about half the letters in a typical piece of English are somehow redundant. And you can kind of test that for yourself. If you just take a piece of English text and you just start blacking out some letters and you ask yourself, can you still tell what the English text said? The answer will be, up until you end up with a bit more than half the letters blacked out, you can very accurately say, oh yeah, I know what that said. Okay, so then the question is, given that we know, so what Shannon's sort of information theory idea was to work out, given knowing the frequencies of letters and blocks of letters and so on, what is the shortest amount of shortest length that you can encode that, shortest thing you can encode that with. So there are two issues. One issue is, can you actually find a way to do that encoding? That's one issue. The other issue is, the encoding we're talking about is an encoding that doesn't know anything about what the text means. Well, let's take these two things in turn. So one question is, can you find the actual shortest encoding? Can you find a procedure? And there are various procedures that are used. So one common procedure is called Huffman coding, and it kind of uses it just sort of has a tree of possibilities, and it's kind of always filling in another branch on the tree for something it hasn't seen before. And the ones it's seen a lot end up being sort of branches at the top of the tree that need less tree branches to get to, so to speak. That's one common method. Another method called LZW encoding or dictionary encoding, and that's used in, for example, programs like Zip or gzip or whatever, and the compression programs on the web. Dictionary encoding works like this. Dictionary encoding says, it kind of is continually making a dictionary. So it says, did I see TH before? Okay, yes, let's give that a name in our dictionary. Did I see THE before? Yes, let me give that a name in my dictionary. Did I see elephant, the letters for elephant before? Yes, let's give that a name in the dictionary. And it arranges it so that things that have been seen before, basically things that are seen often, end up being encoded as short things in the dictionary. Whole blocks of text that have been seen before, the more times they're seen, the more they'll be encoded in the dictionary. And the shorter they'll be encoded in the dictionary. And so that kind of method for something like English text does achieve something close to 50% compression by using this kind of thing where you're making up code words based on dictionary. Another common, very simple method of encoding that is more relevant for, I don't know, let's say you take an image of your screen, okay? The image of the screen, a lot of your screen is really boring. It's just white, for example. Just, in some window, it's just pixel, 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 pixel. They're all got the same color. So there's a method of encoding called run length encoding that deals with that. And what run length encoding does is it says, if you've got many identical copies of the same thing, the way you can encode that is to just say, it's 100 white pixels. So instead of giving white pixel, white pixel, white pixel 100 times, you're just saying it's 100 times white pixel. So that's run length encoding. When you're dealing with images and sounds and so on, there are different methods of encoding that basically use the fact that our human visual system or auditory system doesn't recognize some imperfections. So you can have, sometimes you can just have encoding like I'm talking about for text, where you don't destroy any aspect of the message. It's lossless encoding. You're just kind of using mathematical properties to use shorter code words for one thing than another and so on. But you can also go further than that. And you can say, I really don't need to hear every wiggle in the audio trace, or I really don't need to see every precise pixel in the image. All that I need to see is things that I as a human will recognize. And so, for example, in the case of audio, things that are really high frequency wiggles can be kind of cut out because humans are not going to hear them, and maybe even the loudspeaker on your computer isn't going to play them. So there are methods like that. But in any case, when it comes to just lossless encoding where you're going to be able to precisely get the message back again, there's been sort of a long running story of, can one actually achieve the level of compression that Shannon's results say one should be able to achieve? And there are now codes that do a really good job. I think there are now some codes that are provably achieve that for lots of different cases. And that's been a big story, for example, in the 5G telephony world. There's been, for whatever reason, a big push to get the absolutely optimal codes. It doesn't really matter that much anymore because even codes that aren't perfectly perfect still do really pretty good job at compressing typical signals. Okay, so anyway, that's compression just based on looking at essentially the statistics of how often letters occur, blocks of letters occur, things like that. There's another thing to think about, which is, well, maybe the message actually means something. So let's say you were given the digits of pi, 3.1415926, et cetera, et cetera, et cetera. You might say, to encode 1,000,000 digits of pi, that's going to take me a lot of effort because the digits of pi are kind of random, and I'm going to have to just code each digit with something that represents each of the 10 possibilities, et cetera. That's 1,000,000 things. But actually, in a sense, you might say that's really silly because all I have to do is tell you it's 1,000,000 digits of pi. And that is a very short thing to say and a short thing to transmit. And so long as my receiver understands that it has to essentially run the program of recompute the 1,000,000 digits of pi, I've got a much shorter way to send the message. So this leads us to an idea of what's called algorithmic information theory, where one's asking not what can one compress just by fixed codes, fixed encoding that doesn't know what the message means, but how do you make a program that will produce the thing you were going to say? So in the case of pi, it will be that short program just to compute the digits and so on. Well, so that's sort of the best way to do encoding, is to say, just tell me how to make the thing. Just tell me how to reconstruct the thing at the other end. And actually, even in audio encoding, there's a certain amount of that that's done in MP3, MP4, and so on. It's got all kinds of wild. Actually, well, there are audio encoding methods that are used for phones and so on, where essentially what you're doing is you're modeling the human vocal tract, and you're basically making a program that specifies parameters of how the vocal tract will move, and you're recognizing, oh, this is how the vocal tract of the person who said this moved, and let's essentially simulate that when the message is received. Let's only send the sort of the motion parameters for the vocal tract, and then the other one will reconstruct the actual sound that would have come out of a vocal tract that's moving that way. So this idea that, you know, you basically send the program instead of sending the raw data, that's kind of this sort of ultimate form of compression. So you might ask, okay, so, you know, Claude Shannon had this method of figuring out what the best compression is when you're just sort of given statistical information about the message. What's the best compression that you can get when you're asking for the shortest program that reproduces a message? That was something that was thought about a lot by a good friend of mine named Greg Chaitin. Actually, he did it when he was a high school student in New York City back in the 1960s. He figured out this idea of so-called algorithmic information theory, where you say the amount of information contained in a message is the shortest program that will reproduce that message. So it's a cool idea. The question is, can you actually work out what the length of that shortest program is? And the answer is no. It is in general, it is impossibly hard to do that. In a sense, what you're asking is, and part of the reason is, let's say you say, I want the shortest program. Okay, well, maybe there's an incredibly short program, but it takes 1 billion steps to run to produce the message. If you just start testing programs and say, is this program going to work? Is this program going to work? Well, some of those programs might take an arbitrarily long time to run, even though they would successfully produce your message. So in fact, we know from sort of general theory about computers that in general, you can't in a finite amount of time guarantee to have found the shortest program that will reproduce your particular message. So although algorithmic information content is in principle a really good thing to look at, in practice, unless you say, well, I'm only going to consider computations that take such and such amount of time, you'll never know what the truly shortest program actually is. Now, this question about finding shortest programs is closely related to a lot of things about making models of things. So for example, let's say I'm trying to reproduce, I don't know, what's a good example? I don't know, a tree, for example. And I'm trying to make a model of a tree where I get all the leaves and I'm figuring out how that's all going to work. And I know how the tree is going to behave and so on in different cases. What I want essentially is to have a program that reproduces the behavior of the tree. I want to take the actual tree or my 1,000 trees that I've studied, and I want to say, give me a program that will reproduce aspects of those trees that I care about. And so the problem of making models of things is the same as this problem in a sense of finding shortest programs that represent messages. In the case of modeling, the message is whatever experimental data you picked up. And the program is the sort of the model that specifies how you could reproduce that data theoretically, so to speak. And so then there's a whole kind of question of, you can do things like you can say, well, I've got all this data and I'm going to make a model and it's going to reproduce the data perfectly. Okay, small bug. The model is really complicated. In fact, the model is so complicated that it's basically amounts to just writing down the data and saying, okay, run this program and get the data. Well, you put the data into the program, so not surprising it will get it. So there's this sort of trade-off which comes between how accurate do you want the model to be versus how big do you want the model to be. So the model can be perfectly accurate by just having every bit of the data right there in the model, or the model could be really tiny and get the and be very but be 1% off in reproducing the data. So there's this kind of trade-off between model size and accuracy of reproducing the data that one has to consider, and that's a big issue in a lot of both the sort of philosophical thinking about modeling and in practice in things like machine learning, whether you've really managed to make a true sort of extraction of the essence of the data, or whether you've basically got a neural net or something like that that just has a copy of the data inside it. So anyway, it's kind of a long answer to questions about information theory. I think that the role of information theory as a way to understand sort of compression and things like that is something that's baked deep into our kind of way of doing things we do with data and computing. I think that these ideas about sort of the algorithmic character of information is sort of poorly captured. And people sometimes imagine that there's kind of a magic to information theory that says, yes, it's the true information content of a message, what we get from, Shannon's formula and so on. It's not. In the case of pi, for example, it will give you completely the wrong answer for most practical cases. It's not accounting for the fact that the message actually came from somewhere. There was a thing that produced it somehow. And if you can model that thing, if you can have a program that represents what that thing does, you can potentially say much more simply, you can have a much shorter description of what goes on. Now, I have to say that in my own efforts in science, one of the things that I've discovered is that even things that have very small programs can be very complicated. You might imagine that if you have a small program that you could only get some behavior that would be quite simple. You'd get this little program, you run it, and it would just, go 1 0 1 0 1 0, repeating all the time. But actually, what we know from stuff basically I worked on in the 1980s and beyond is that isn't true. That even with very tiny programs, even with programs you kind of just pick at random and small programs, you can end up with these immensely complicated behavior. And I think it's a very important phenomenon. It's a phenomenon that's probably the reason why in nature we see so many things that look to us complicated. It's the same kind of idea. Nature is just picking a simple program at random and producing things that look complicated, and where the Shannon information content, so to speak, will be very large, even though the algorithmic information content, in fact, is just this tiny program. So it's a little bit misleading sometimes, and people sometimes kind of imagine that because there's this kind of mathematical theory of information, that it's kind of the whole story of what is the true content, the true information content of a thing. That's not really right. It's better to think about that in terms of how would you make the thing from a program and so on. All right. Oh boy, lots and lots of questions here. Oh my. Question from Adam here. What books and exercises are best to take from a high school level physics, mathematics understanding to be able to make sense of the Wolfram physics project model? I guess I would pitch my own writings on wolframphysics.org. I tried to write kind of an introduction, both a kind of a quick introduction and a 400-page introduction that I think goes sort of step by step. I'd recommend looking at that. I'd also recommend, there's a piece of software tools. I'd recommend looking at the tutorial there, which allows you to actually run all the code and try for yourself, actually run the things and see how it works. Okay, there's a question from Jack Bound here. Why is the core of the Earth as hot as the surface of the sun? Is it fusion or fission? Is this true of many planets and moons in our solar system? Okay, astrophysics-y type question. All right, so first question is, it's kind of a surprising fact that the Earth is hot inside. How do we even know that the Earth is hot inside? Well, volcanoes are kind of a clue, but people, when you drill a hole deep into the Earth, the deeper you go, the hotter it gets. We also know that the Earth is liquid inside. And the reason we know the Earth is liquid inside is because when an earthquake happens, it produces a big, it wobbles the Earth. And by looking at essentially the waves that are generated by, an earthquake happens, it wobbles the Earth, that produces waves that propagate through the Earth. And by looking at those how those waves propagate through the Earth, we can tell what's inside the Earth. Actually, there are two kinds of earthquake waves. There are ones that go along the surface, where basically the surface of the Earth is wiggling up and down, and there are ones that go through the interior of the Earth, where you're getting compression, expansion, like a sound wave, except that it's going through rock. And those waves arrive at different speeds. Typically, the ones that are really kind of the bad news for a building or something like that are the shear waves, the ones on the surface that make things go up and down a lot. But and the ones that go through the interior of the Earth arrive more quickly than those ones. So the way that we know that the Earth has a molten core is that we've been able to see those seismic waves going through the Earth, and we've been able to tell that they have the characteristics of going through a liquid rather than a solid. In fact, we also know that right in the very center of the Earth, there's a piece of solid core, because there are some seismic waves. If we have an earthquake that happens on one side of the Earth, by the way, I mean, the Earth is kind of rigid enough that an earthquake happening anywhere on the Earth produces some vibrations anywhere else on the Earth. And so if you have a seismometer, it's basically just a sort of the simplest form. It's just sort of a carefully balanced weight that every time sort of the Earth bounces up and down, the weight doesn't move, and so it relative to the Earth, relative to the sort of the casing of the seismometer, it's moving, and then you can get a trace on it. It used to be a pen trace. Nowadays, I'm sure they're all digital. But in any case, a seismometer has if you have a seismometer anywhere on the Earth, you can detect basically any real earthquake that happens anywhere on the Earth. You can also detect, for example, any nuclear explosion anywhere on the Earth quite easily with seismometers. And actually, in modern times, there's kind of a cool new method of dealing with seismometers, which is if you use the fiber optic cables that are used for communications, when you have a compression wave going through the Earth, the length of the fiber optic cable is going to change slightly, and so you can, or rather so by using sort of the network of fiber optic cables and using ones that aren't actually being used for communication, you can make potentially a very sensitive seismometer, and one that can actually detect sort of motion before an ordinary seismometer would detect motion and potentially actually predict earthquakes and things like that a little bit faster, or at least know when an earthquake has happened a little bit faster. In any case, the Earth has a molten core. The very center of the Earth happens to be solid. Why does it get to be that way? Well, as you go deeper and deeper in the Earth, there's also higher and higher pressure. So when you have something, well, let's say like water or anything else, you're trying to make it. You've got ice. You heat it up. It turns into liquid water and so on. But if you were to squash it really hard with high pressure, then it won't become molten as it won't turn into liquid as easily, because you're pushing the atoms together, so they're still stuck together in a solid. They can't wiggle. They can't move around freely like they do in a liquid. So when the pressure goes up, things tend to make solids even when the temperature is higher, and that's what's happening at the center of the Earth, among other things. There's also a segregation of actual materials, but different reasons. But let's not go into that right now. But in any case, so the Earth has a liquid core. Why is the Earth hot inside? There are two different effects that make the Earth hot inside, and they're probably of about equal importance. One reason why the Earth is hot inside is because it started that way. When the Earth was originally formed 4.5 billion years ago, it was formed by lots of little pieces of rock and other things all crashing together. And that process they were pulled together by gravity. And so things were falling onto the Earth as it was forming. And as they fall, they're converting all that energy into heat. And so as the Earth formed, the inside of the Earth will have been hot. And so then the question is, in 4.5 billion years, does heat manage to get out of the Earth? Or does it stay sort of trapped inside the Earth? And the answer is the rate at which heat is sort of conducted through rock is such that some of it still stays inside the Earth. I mean, the fact is that if at the surface of the Earth, we have every day, every night, the temperature goes up and down, the air temperature increases and decreases. If you drill a hole down, you don't have to go very deep in the soil before the temperature is pretty much constant throughout the year. Maybe 50 degrees, I found it Fahrenheit, I think, is a common temperature. That is some kind of average temperature that you get to not very deep in the ground. So in 4.5 billion years, the heat of the inside of the Earth hasn't really been able to be released. It's still sort of trying to get sort of transmitted through the rock that makes up the Earth. So that's one part of where the heat of the Earth comes from. The other part of where the heat of the Earth comes from is a completely different effect, which is the decay of radioactive elements. So when the Earth was formed, it had all the different chemical elements, all 90 or so different kinds of stable elements, mostly, because if an element was unstable, if an element is such that something like plutonium, let's say, where it decays quickly, so its nucleus just self-destructs, and it might decay in a millionth of a second, or it might decay in a second, or whatever. But anything that decays in a second, even if it was there at some point, is long gone. In 4.5 billion years, it's really gone, seriously gone. If half of it is gone in a second, then in 4.5 billion years, it's really gone. Okay, so when the Earth was formed, some of the this is getting into a different issue, which is where the elements in the Earth come from. And the very hydrogen, helium, lithium, beryllium, all these successive elements have successively more protons and neutrons in their nuclei. And when the universe was formed in the Big Bang, when the expansion of the universe started up 14 billion years ago, that process where the universe was very, very hot at the beginning, gradually cooled down. In this very hot early universe, some chemical elements easily get made. Hydrogen is there, about a quarter of the universe is then helium, and then successive elements get made with lower and lower probabilities as you go down the list of elements. And a little bit of details about how different nuclear reactions happen, cause different elements have different abundances. But basically, that process of kind of jamming, what's happening in that case is you're jamming atomic nuclei together, and they're fusing, and you can get elements up to iron that way. You can by basically just fusing things together. That's something where when they come together, they stick, and there you've got a heavier element. So up to about iron, you get that. To get beyond iron, you need different processes. The most common process is a supernova. When a star explodes, you generate this whole sequence of heavier elements because there are other processes that can occur and that are sort of much more violent than happened in the early universe, and or at least at that stage of the early universe. And in fact, all the heavy elements that exist on the Earth come from things like supernovas. So anything like gold, for example, has to have come. It didn't get made at the beginning of the universe. It got made in something like a supernova. So when supernovas happen and make those heavier elements, some of the elements they make are things like uranium-235. The feature of that is that it does decay, but it decays very slowly. It takes half of, if you have a sample of it, about half of it is decayed in like 1 billion years. Okay, so that means that when that element or isotope of the element got incorporated into the early Earth, it's there, it's stable enough that it managed to make it to actually be transported from somewhere else, and it formed in the, as the star, as the sun formed, as the Earth formed, took, hundreds of millions, billions of years for all that to happen, hundreds of millions of years, more like, or even perhaps less than that for the formation process. But in any case, the thing was able to be transported wherever it was made to where we are. It's all good. And it eventually gets incorporated into the Earth. But when it's in the Earth, it's decaying. And when that uranium-235 decays, so the nucleus is, it's sitting there as a nucleus, and then kaboom, it breaks itself in two pieces, for example. And those two pieces, it releases energy when it does that. And so those two pieces kind of zoom off with pretty high energy. And that energy is then turned into heat. And so part of the heat of the Earth is a consequence of the decay of radioactive elements. And I think the current belief is that about half of the heat of the Earth is due to the decay of radioactive elements, and half is due to a remnant heat from the formation of the Earth. Okay, so how do these processes work for different kinds of things? Well, if you have a very small thing, even the moon, for example, there may have been enough time that whatever heat there was when the moon was formed has managed to escape from the moon. And so it doesn't, so in other words, the moon has completely solidified. In fact, we know that that's the case, that the moon does not have a liquid core. The moon is solid all the way through. As you get up to different planets, I think Mars may have a tiny liquid core. I'm not sure if that's, people have looked for Mars quakes. I'm not sure if that's, the last I remember, I think it may have a tiny one. We don't know in all other cases, and something like Jupiter is a more complicated case because Jupiter is a much bigger planet and its core is probably solid hydrogen, and it's a slightly different story. But in any case, so something like one of the small asteroids or something, it definitely doesn't have a liquid core, because in the time since it was formed, there's been more than enough time for sort of the heat to get out from the center and the whole thing to solidify. So let's see. I think that that's the story of what. So I don't know. It's a good question. I should know the answer. I don't. How long in the history of the Earth it will be before the core of the Earth has solidified? I don't know the answer to that. I would guess quite a long time. I would guess many times the time the Earth has already been around. I mean, the liquid core of the Earth is responsible for things like the magnetic field of the Earth, and that moves around as sort of currents in the mantle of the Earth. The liquid part of the Earth move around. Okay, let's see. Oh gosh, so many questions. This is all right, we'll do a completely different kind of question. There's a question here from Parmenides. What good and bad aspects are there to being financially successful? How did my life change when I first became a millionaire? Gosh, I've never thought of myself as that. I mean, yes, I've run a successful company for a third of a century now. Although I would say that my main objective is to make interesting things and make interesting things happen. And I see sort of financial success as being something necessary to achieve that goal, not a very interesting goal in its own right. I mean, gosh, I think that the main, for me, and I don't think different people have completely different motivations for things. For me, the main sort of objective of making money is to be able to do interesting things, do projects that I want to do, and those kinds of things. I mean, our physics project, for example, is not particularly expensive, but it involves some people and resources and computers and all that kind of thing. And that project is something which, because of a certain degree of financial success, I don't have to think about how much that project costs. If I wanted to scale it up and have, hundreds and hundreds of people working on it, be a different story. But at the scale of a few people and machines and so on, it's like, yes, we can do that. It's not difficult to do that. I would say that the main thing, as far as I'm concerned, is what possible things you can do, that how to be able to do the things you want to do, how to turn ideas you have into real things. Sometimes using money is useful in turning ideas into real things. Sometimes it's not really a question of money. It's a question of figuring out more stuff. You can throw as much money as you want at it. It's not going to help. I myself in my particular life have kind of tried to sort of make enough money to do the things that I want to do, but I have not been particularly interested in the pure goal of making money. That's in a sense, there's a sort of a trade-off sometimes between you can do things which are, to me, less intellectually interesting, but make more money. And it's like, why would I do that? I'm interested in doing the things that I find interesting, so to speak. And the pure act of making money is not one that I happen to find terribly interesting. I think that, I have to say, as a matter of observing the world, that money has positive value and money also has negative value. And I see just so many cases where one ends up seeing kind of the negative value of money, not necessarily for a person themselves, but for people around them, for the organizations around them. You take a company and you give it too much money. All sorts of terrible things happen. You would think that fantastic, the company has too much money. Well, it turns out it starts doing crazy things, and it starts doing things that ultimately are very counterproductive and so on in many cases. I often am aware of this kind of negative value of money thing, which is one reason that, at least in my own life, I've kind of, tried to make enough money to do the things that I want to do, but not money that kind of I don't know what to do with, so to speak. And that's always a challenge, because sometimes I have many friends who made lots of money, and sometimes you intend to make a certain amount of money and you overrun and you make a lot more. And then what are you going to do with this money? Well, you want to give it away in some responsible fashion, but that's a lot of work. And sometimes, it's as much work to sort of spend money responsibly as it is often to make money. And so I think that's it's a complicated thing. I think that, the issue is when you want to do a project, when you want to do something, it's like, are you held back by the fact that it's going to cost too much money and you don't have that money? Or is it something where you can say, sure, I can do that? Now, if I look at myself, there are projects that, sure, I might be interested in doing them, but they cost way too much money. But I'm not even sure that money is the real issue. I mean, you know, maybe I'm interested in something to do with making molecular scale, building things on molecular scales, making kind of sort of making a whole engineering technology on molecular scales. I've been interested in that for a long time. And I might say, well, let's pour some money into that. And, you know, we'll build this giant lab and we'll do all these things. But honestly, that's not the problem. The problem is I don't know how to do it. It's not that we need to spend $100 million to build the lab and build all this stuff. It's we don't know how to do it. And yes, we could get a bunch of people to start researching how to do it. But honestly, I think it needs some core ideas that I don't think we have. And it's not a money limited problem. I mean, and even in the case of, you know, in a very, very elementary case, you know, we run these summer camps for high school students. I recommend them to anybody who's of the right in the right demographic who's here. But you know, I've been interested in providing scholarships for those, et cetera, et cetera, et cetera. Turns out it's actually hard to spend that money in some sense, because the people for whom that would be a wonderful match of come to our summer camp, we'll pay for it, et cetera, et cetera, et cetera, aren't the people who know that the summer camp is happening or know that that financial aid is available. And so there's a completely different problem that has nothing to do with money. That is, you know, is a sort of problem of communication and sort of the way that things are stratified, unfortunately, in the world, that make it difficult to have that communication. And it's not just a question of money. I mean, you could throw, you know, I could say, okay, I'll spend X amount of money to solve that problem. I don't know what I would do. I don't know what to do to solve that problem with money, so to speak. I mean, I could think of a few things, but they're just a complete waste of money, and they would have a, you know, their fractional return would be just absurdly small, and it's really like a pure waste. But so that's I mean, I would say that the at a very you know, I've been fortunate enough that you know, I started doing things with companies and so on very early in my life, and so I've been I've usually been in the situation where I make more money than I personally find easy ways to spend, and so I'm not and I think I don't pay that much attention to you know, it's not my yeah, so I don't think it's made that much. I mean, as a practical matter, you know, I have a nice, comfortable life, so to speak, which probably helps a lot in being productive, in thinking about things and doing science and so on. I mean, it's like there are probably things where I have delegated them to other people and other people do them for themselves, and I'm like, it's a better calculation for me to make some more money and spend the money getting somebody else to do that than to do it myself. Of course, you know, it's amazing how much stuff, you know, that's again a complicated trade-off, because there are things where, you know, I've had lots of experience about doing certain kinds of things, and it's like I'm pretty efficient at doing them. And there's a question of, is it better to have somebody else to delegate that to somebody else? It costs some money, but if you don't worry about that money, you're delegating something to somebody else. But the question is, you know, they may not be as experienced as you are. They may not be as good at doing that particular thing as you are. What's the trade-off between what should you delegate and what should you just do yourself? And sometimes I end up doing things, and it's a sort of a shocking activity for a CEO like me, but I like to try to understand what, you know, how things in our company work. And sometimes there are problems where it's like, look, I can just solve that problem. Other people will spend days, weeks trying to solve it. It's going to take me a limited time. I might as well just solve it. I'm reminded particularly a few weeks ago of a problem that was admittedly a bit frustrating, was the connectivity of our, so we have a whole cloud infrastructure system, and some part of it lost its connection to the outside world. So that meant that some operations that people were doing with the cloud just didn't work. And so the very good team that we have that deals with these kinds of things was trying to solve this problem. And a few hours went by and they still hadn't solved the problem. And so I'm like, okay, look, let me look at this because I think I might be able to solve it. So I dig into this, and 2 or 3 hours later, we'd solved the problem. It was sort of an interesting problem to solve. It was very tricky, actually. It had to do with, packets of information being sent over the internet, and some packets would arrive, other ones would not arrive. There's a certain, always on the internet, about 1 or 2% of every packet of information that's sent on the internet just doesn't arrive. It's kind of a shockingly, bad system in a sense. But the way the internet is built, the system, the thing that what happens is a packet is sent, a packet is then there's a receipt sent back if the packet arrives. If there's no receipt that's received, the packet is resent, and that's the TCP protocol. And in any case, in this particular case, some packets were just many more than 2% of packets of certain kinds of packets were just disappearing. And I figured out, it was just a question of doing a bit of data analysis, of looking at, here are a whole bunch of packets. What happens to different packets? Oh, these packets that are going to this particular, going on this particular fiber backbone to this particular internet backbone provider are not being delivered properly, but ones to another provider are being delivered, et cetera, et cetera, et cetera. And end result, okay, here's the problem, and then we go and fix it. And I at some level, it's like, it's a bit frustrating to be like, gosh, we've got, many layers of very capable people, and why aren't I delegating this problem to be solved? But the fact was, in the end, I don't know how long it would have taken to solve this problem. It might have taken a week to solve this problem. I think that sort of some additional experience, plus in that particular case, some facility with tools, particularly our Wolfram language tools for exploring these kinds of things, was super useful in debugging what was going on. And anyway, it felt like it was a sign of, it's a little bit of non-helplessness, so to speak, in the sense that I can actually go and debug this kind of thing myself if I really need to. All right. There's a question from user temporarily suspended. Okay, that's an interesting handle. If you got a chance to talk to Richard Feynman right now in 2020 and ask only one question, what would it be? I asked a lot of questions to Dick Feynman while he was alive. I think, let me see. The question is, did I learn enough from him that I think I could sort of predict his response to any question? Or are there questions where I wouldn't know his response and really would want to ask it? I think that, there are historical questions of curiosity that I have, but I don't think those rise to such a level of importance. I think that I would have to yak on for a while, telling him about what we figured out in our physics project and so on. And I think he'd be very, very excited about that. I think there are many things that we've managed to resolve that he wondered about for a long, long, long time. And I think that he took computers very seriously and thought that computation was an important kind of thing to think about. But sort of the connections that we managed to find to physics, I think, would not entirely surprise him, but he would find very satisfying. And for example, one particular question about, I think the path integral of quantum mechanics that he invented, we've kind of figured out sort of how that works and how it relates to Einstein's equations in general relativity and so on. I think he would find that I can kind of remembering him, I can kind of think of actual words he would use to express his excitement for that connection, because I think he would find that connection really, really quite amazing. And I know what he would ask me. He would ask me, did you solve the problem of why e to the IHT, why it's e to the IHT and e to the minus beta h? So the e to the IHT is a formula in quantum mechanics that represents the time evolution of a system in quantum mechanics, and e to the minus beta h is a formula that represents the statistical probabilities in thermodynamics and statistical mechanics. And I talked to him for ages and ages about why are they both exponentials of the same form with the same dependence on the energy function and so on. And he's like, there's got to be a way to do this. There's got to be a way to understand why this works this way. It's not a coincidence, et cetera, et cetera, et cetera. I think we now know how that works. I think another thing that he always used to ask is one of the techniques he invented, these things called Feynman diagrams. So Feynman diagrams, if you're looking at, for example, an electron, the scattering of one electron by another. So you shoot two electrons at each other and they have an electric charge, and they also have at a quantum mechanical level, you think of them as exchanging virtual photons. And so there's all these processes where the things will scatter because one of them generated a virtual photon and that hit the other one and that pushed the other one and so on. And there are all these sort of separate processes where they can exchange not one virtual photon, but two virtual photons, or a virtual photon that turns into a virtual electron-positron pair, turns back into a virtual photon. There are all these different ways microscopically that scattering process can happen. And one of the things Dick Feynman did was to invent this method called Feynman diagrams, which was a way to compute the probabilities of all those different little sort of ways that scattering can happen. And so one of the things is that if you want to get a rough estimate of what the scattering probability is, you can just consider a few processes and a few diagrams. If you want to get it more accurate, you start having to consider thousands of diagrams, tens of thousands, millions of diagrams, and so on. And one of the things that, and each one of those diagrams is a huge amount of computer effort to compute what the probability implied by that diagram is. It's a very nice, interesting kind of computational thing to do, but it's very complicated. And so Dick Feynman, even though he invented this method, always used to say, it's the stupidest method. You know, the fact you have to go to so much effort to work these things out, it's just crazy. And by the way, you might have 1,000 diagrams with all kinds of detailed, complicated integrals and all this kind of thing. And the answer is 17 pi squared over 6 or something. All these different pieces all add together and eventually get a simple answer. And that should be kind of a clue that all these diagrams weren't necessary, that there was a simpler way to get to that answer. But nobody's ever found it. There's some hopes from some mathematical methods that come out of string theory that there might be a way to sort of have a simpler way to deduce what the results from these Feynman diagram calculations are, but that hasn't yet worked out. But that's one of the things that was one of the kind of the unfinished pieces of business from Dick Feynman was these Feynman diagram things that he invented. He's like, these are really stupid. There's got to be a better way to do this. But we don't know it yet. And the methods that we've invented don't directly give us any particular insight that I know of. I'm actually quite sure. I haven't really thought about that. Good question. There's the buzzword for a bunch of the sort of new approach to these things is a thing called the amplitudahedron. I think we've had some thoughts about how the amplitudahedron relates to some of the things that we're looking at in our models, but this would get highly technical to talk about. Well, now let me not try. Anyway, so the answer is I don't have a really good answer to your question, I'm afraid. Okay, there's a question from Saul here. Is it easy to make a bot for every video game? And how good can anti-bot detection methods be? Well, first an admission from me. I really have never played video games. I kind of wrote a little tiny computer game back in like 1973 that was incredibly trivial, and I never found it that interesting, and I haven't really played video games since. My awareness of that world comes from building some tools that get used there and from knowing a lot of people who are involved in that world. So I'm less up on exactly what happens in video games these days than I probably should be. It's a blind spot of mine. But the real question is, if you've got an entity in a video game and it's pretending that it's a human at the other end of the line, so to speak, can you tell? Well, first of all, can you build something which will emulate human level performance in the game? And second of all, if you've got this player in the game, can you tell if that player has an actual human underneath it, or did it merely have a human programmer and it's a bot? Does it have a human sort of puppeting it in real time, or is it something where there's no human still in the loop. So I don't really know the answer to whether, to what extent it's possible to make a bot that successfully achieves sort of human level play in video games. It's been a long running question. If we look at different kinds of games, whether it's chess or Go or backgammon or whatever else, at what point can we make a computer that will achieve sort of human levels of play? And in those games, the main issue is there are lots of possible things that can happen in the game. Can you kind of figure out what all the possibilities for what could happen are? Can you see 6 moves in the future, what all the millions and millions of possibilities are, and say, look, the chances are if I make this move, that will lead to the best outcome 6 moves from now. And that's kind of been the main approach that's been used in kind of getting sort of human level play in these non-video games like chess and so on. I think that in a sense, there's a question of how human or non-human is that process. In other words, when human chess players are doing their thing, to what extent are they in their minds sort of working out all these possibilities, and to what extent are they using quite different heuristics, quite different ways of guessing what should be done, and quite different kinds of intuition that they can't necessarily explain about what to do. But the computer way is very much sort of, let's just see what could possibly happen and then pick the move that will, with best probability, give me a good outcome 6 moves in the future. Okay, so to what extent can that be done in video games? I do not know. I think that actually, now that I think about it, yeah, we even we've done experiments with machine learning on simple video games, like sort of 8-bit video games from the ancient 1980s or something, and I think that there are methods, so-called reinforcement learning methods, that do okay at playing those games. In fact, now that I think about it, I was at the demo, sort of the first public demo given of a very sort of a supposedly very impressive AI system that was playing 8-bit video games. And actually I somehow was a medium-sized group, and somehow the person organizing it, somebody gave this grand demo. This was a company called DeepMind that was sort of their first public demo of these things. And so the organizer of this thing kind of shows this demo, and then after the demo kind of happens to turn to me and say, okay, was that impressive or not? And I'm like, well, I don't really know, because I just don't know how hard it is to play that game. And, it's, and that's a common issue is, I remember many years ago, a person who worked in the group I ran did the first sort of neural network approach to playing backgammon. And I was like, I'm looking at these things he's doing, and I was like, I have no idea how, is this impressive? Is this not impressive? I have no idea, because I don't know how hard I don't really know how hard this problem is. So in any case, a certain amount of success has been achieved using very straightforward reinforcement learning techniques. What is reinforcement learning? Basically, the idea is, in general, what you're doing in machine learning is you give a bunch of examples, and then you say to the machine, okay, you've seen these examples. Now I'm going to show you a new thing. What is the example? Okay, with a bunch of examples, you say, this is an example of pictures of dogs. This is an example of pictures of cats. Now you show the machine a picture, and you say, based on those examples you saw, is it a cat or a dog? And so the machine has to kind of statistically work out, based on all the examples it saw, what's the likelihood? Is it a cat or a dog? Okay, so reinforcement learning, the idea is that the machine is sort of probing the world to find out what would happen if this, if you did this, what happens? In other words, rather than you surfacing, rather than you just giving it, here are a bunch of examples, now learn from those, it's like the machine is generating its own examples by saying, well, if I move like this, what will happen? If my opponent, if I do this, what will my opponent do, et cetera, et cetera, et cetera. And so that's a sort of a pattern for doing machine learning. And I think one can achieve a certain degree of success. I don't think it's like slam dunk amazing. And I think with more complex video games, it probably gets much more difficult. And my guess is that the sort of treeing out of possibilities for something like chess, there's only a discrete set of possible places where you can put pieces on the board. In a video game, you can move that Mario character or something. It's about my level of video game knowledge. To a particular place, and which pixel do you get to? What else was happening in the game? It's not a finite situation in the same way, a discrete situation in the same way that it is with something like chess. It's much harder to sort of tree out all the possibilities. So my guess is it's not that easy to build a bot that does a really good job of navigating a typical modern complex video game. And I think that's kind of in fact, now that I think about it, I've seen a bunch of demos of these kinds of things, and none of them have been all that impressive. So, and I think the extent to which you need to do, that it's difficult to do that is also the extent to which if you said, well, I just want a bot that's going to answer my email for me. Well, insofar as video games are a good model of the world, it's sort of the same problem to play a video game well. It's like, can you actually navigate things that are sort of like the real world? And that's difficult because it depends on a lot of things that are kind of built-in cultural knowledge of humans that go back a long way and so on, and are not easy to sort of expect to encode in a kind of one-shot, I'm just built to play a video game kind of device. If you're kind of emulating everything the human does, it's a different story, but I doubt that it's something that's possible based on kind of just the pure, I'm going to build this thing to play a video game and that's it. So question of whether you can tell whether something is a bot or a human, that's an interesting and challenging thing. There's a general question of, can you tell if something is an artifact or something is a thing that was just made by nature? Can you tell if something was done on purpose? Can you tell if something was done as a program as opposed to by a person? I think that's the story. You go to your average website and you try and do one of those captures. So it's like, well, there are these letters and they're distorted in this way. Can you read what these letters say? Is that something a human can do? I often find those things pretty difficult to decode. What on earth is this letter? And then I don't even know whether they care about, actually, I should learn this once and for all, whether these things care about capital or lowercase, the distinction between those things. But anyway, it's sometimes really hard. You see an X. I don't know if that's supposed to be a capital X or lowercase x. I have no idea. I don't know whether it cares what I type in. But anyway, so that's a case where you're trying to have something which is doable by a human, but not doable by a machine. And similarly, these things saying, find all the bicycles in this picture or something, are again, things which are kind of sort of doable by humans, but not by machines, except those are increasingly doable by machine. And my guess is that most of those things, so if you define a specific task like that, it's probably the case that you can make a machine, successfully train it to do that particular task. This is the general question of, are you a bot or a human? A common version of this is this idea of Alan Turing's from 1950, the Turing test, where kind of the question is, if you sat down at a computer and, well, he didn't think of it that way because he didn't know about computers that way, but he just says, you're asking questions to a thing. And the question is the thing a human or is the thing a computer? And the issue is, what questions do you ask to tell whether it's a human or a computer? And, so people have tried to make sort of conversation bots that try to fool people about thinking that, oh no, it's really a human, not just a bot. It hasn't worked very well. But somehow, if you say, what's a systematic method of testing? It's actually fairly hard to come up with a systematic method of testing, because in a sense, that systematic test has to itself be as good as the bot that you are trying to produce, so to speak. So one giveaway, there are a bunch of these bots which use Wolfram Alpha as their source of computational knowledge about the world. And so one absolute giveaway is you just ask these bizarre different questions about different things in the world. If it can answer all of those, it's not a human. No human can do that. No human knows these different diverse things with precision in the way that, you can just look them up in Wolfram Alpha. So that's kind of a weird way to conclude that, because you might think, oh, the human will be much more capable than any computer, but not in that way, at least. And so it's a really interesting question. If you people at different times have put up these various chatbots, I have to say that the very early chatbot was this thing called ELIZA that was done even in the 1960s, and it was kind of an imitation of a sort of psychologist talking to a person, and the bot would say, I don't know, would say something. You make a statement. I like the color orange. No, that would be a bad statement to make. Something like, I ate an apple at lunchtime today. And it would then say, how do you feel about eating an apple at lunchtime? And, there's a sort of a question of how realistically sort of human does that end up being? Something that's interesting about that is it's pretty non-convincing pretty quickly. But one thing that's sort of interesting is that even though it's somehow non-convincing, it doesn't mean that we don't respond to it in some way as sort of humans with emotional responses. I mean, it's just like, I don't know, there are situations in which we are, in which we're confronted with something that is not the real thing with its whole story, but is sort of an imitation that still makes us feel. I mean, I don't know, we have, what's a good example? A bad example would be something like, plastic wood. You can have something where, well, you think, it's a wooden surface, that's all very nice, it has some particular meaning, but, oh no, you have a plastic, wood that just plastic that is, wood textured, so to speak. Well, that's kind of, we still might feel pretty good about that in certain situations, even though it doesn't really have the whole story behind it's the fine wooden surface, so to speak. And I think that it's the same kind of thing that happens with these chatbots, that even though we kind of know that it's not a real thing, it kind of elicits certain kinds of responses in us that are sort of real to us, even though we know the thing that's eliciting them is not, well, here's a good example actually of something a little bit like that. If you have, a fire alarm or a siren or something like this, those sounds sort of plug into probably very basic circuits in our brains that are like, no, that was something crying out in some person crying out in some way. It captures some essence of those sounds. And so we pay attention to it and we respond emotionally to it, even though we perfectly well know that's just, an alarm system or something. So I think the same is true to some extent with chatbots, even though they don't really achieve the full sort of human level, you could really not tell that it isn't a human. It's still something which we respond to in some kind of way. But I think it's an interesting question whether it's sort of a systematic way to tell whether the Turing test is being passed. Well, but that sort of requires having passed the Turing test. And I think it's kind of it's like saying, how do we verify that this program is doing what we want it to do? Oh, we need to have written another program that says what we want it to do. Well, but we just wrote a program that tells it what we want it to do. So it doesn't really get you anywhere. Okay, many questions here, and I'm almost out of time, completely out of time. Let's see. A detailed comment from Icy here saying that it'd be nice to have a zip file of all notebooks from the Wolfram Physics Project Technical Introduction. That's a good suggestion. Hopefully somebody in my team can note that down. Let's see. There's a question. Okay, I'll do one more here. There's a bunch of physics questions which are perfectly interesting, but I can't cover all of these today. Question from, and I'll save them up for next time. Question from Fabry. It's a question about outreach to students and helping people succeed and increasing outreach that one does to students. As I was sort of explaining before, the challenge is reaching the right people. I mean, even, this live stream, I have no idea whether we're reaching all the people. I'm sure we're not reaching all the people and students and so on who might find this interesting. I'd love to get ideas about how to reach those people. It's it can be awfully challenging because people, it's so, there's sort of so much, there's a great extent to which people sort of don't understand, people, particularly young people, how do they know what's out there in the world to do? Unless somebody tells them, it's really hard for them to know. Now you might say, well, they'll just find it on the web. Well, yes, at least in these days, that's possible. But still, you have to kind of have the idea that there might be something like that out there. I mean, there are plenty of times where I realize, I don't know, I've been doing historical research recently about a particular topic I can talk about another time, where, I'm continually like, really, are there actually scans of phone books from Moscow in the 1930s? Well, maybe there are, but I sort of just didn't know that was out there. But I know enough to know to look to see whether it's out there, as opposed to just, I couldn't possibly know whether there was somebody in a Moscow phone book in the 1930s, so to speak. So I think that there's sort of a challenge of even if one provides a bunch of resources, how does one actually, how do the people who are relevant to take advantage of those resources get access to them? And from my point of view, as I say, we have our summer camp for high school students. Actually, just yesterday was thinking about that in connection with the fact that we have just a terrific group of students who come every year. I mean, different ones every year, but in a sense, our criteria for these students probably exclude some students for whom it really would be a good thing, but they're not nearly as prepared as the other students. And this is sort of a common problem in educational settings, that there might be students where it would really be an important and worthwhile thing for that student to be pulled into this educational setting, but they're not really quite ready for it. And they need to do some other stuff first, but then you've got a whole bunch of other people who are ready, and you don't want to kind of hold those people back and so on. So you have to kind of invent some kind of segmented approach, and I'm trying to think about how to do that. That deals with kind of having a way to have people who are much better prepared and can just jump right into sort of one program of education, and then people who are less well prepared and who can jump into another one. And sometimes there's a challenge because not only do people not know content, they also sort of just don't have the idea that, of doing projects, of sort of learning things in a particular way. I don't know how to learn stuff. I don't know how to do a project, those kinds of things, which are sort of different problems. Personally, I find those, I find those, I think, very valuable things to communicate, but they usually have to be communicated experientially, like I don't know how to do a project. So I'll tell you something about doing projects. So, for whatever reason, when I was pretty young, I got into this kind of perhaps egotistical point of view that I'm much more interested in doing projects that nobody's ever done before than in doing exercises that lots of people have already done, okay? Maybe it's a piece of personal sort of egotism that I want to do something special. But that was, a point of view that I had from very early on. And then it was like, well, what problems, should I try to solve that people haven't solved before or whatever? What projects should I try to do? And it's like, well, I mean, I just started, well, this is interesting. Let me go try and figure this out. I don't think I have, to my great surprise, because I just sort of thought everybody always does that. I don't think it's so common. People just think, oh, if it hasn't been done before, it must be impossible. That's not my point of view. My point of view tends to be, if it hasn't been done before, well, nobody got around to doing it. It doesn't mean it's necessarily, it certainly doesn't mean it's impossible. It doesn't even necessarily mean it's terribly hard. It just means for whatever reason, people were pointed in some direction, nobody got around to doing it, it hasn't been done. So, but I think this idea that you can just invent something and then just sort of turn it into something that becomes real in the world is not something that people are as familiar with seeing, and particularly not kids. I mean, I've noticed that, one of the things that it's always if you name products after yourself, like Wolfram Alpha, for example, that has all kinds of very bizarre consequences. Some of them are kind of fun, some of them are a little annoying, but one of the ones that I find particularly charming is this. I'll go and I'll give some talk to some group of students somewhere, and they know my name, and it's kind of like, oh, they suddenly realize to ask, oh, are you something to do with that Wolfram Alpha thing? And it's like, well, yes, yes, that's my thing, so to speak. And they're like, oh, that's interesting. And you can kind of, for me, it's like wheels are turning. Not that, oh, there's this guy who did this thing, who cares? It's rather this general notion that behind this thing that people use on the web and it just sort of exists out there is an actual person who decided to do it and decided to build this thing and went from nothing to actually a thing that was built that people use out there in the world. And I think this notion that one can go from nothing to something, and that's a thing people can do, is something that unfortunately, a minority of people, particularly kids, really understand that point. And it's a very empowering point to understand that, everything was, that we have in software, whatever else, ideas, they were invented by somebody. And it's not like it's off. Even for myself, any field that I don't know about, I at first kind of think, oh, they invented this. Some out there in the kind of distant mists of whatever, they invented this. And then as I've studied history of science and things like that, it's like, oh, this person with this whole history invented this because of this and this and this, and they were in the right place and knew the right things to invent this. And it all feels a lot more personally doable, so to speak, after sort of that chain of things that happened and so on. And I think that's a piece to sort of empowering people to understand that point. And I, as a sort of hobby, I've done a certain amount of, I do two kinds of mentoring, CEOs and kids. And they have a charming similarity, actually. I mean, which is that they both, at least the ones I find interesting, they both have the feature that they take the point of view that anything is possible. Some CEO of some company is like, well, yeah, we can do that. Let's go and build this piece out to our company, and I'll get et cetera, et cetera, et cetera. And similarly, kids, at an early stage in life, it's like, yes, it's possible that I can do this and become that, and so on and so on and so on. And those things are kind of fun. And I find it, for me personally, I find it really quite interesting. And it is very charming to the extent to which the issues between kids, particularly kids in slightly complicated circumstances, and CEOs are the same. And they're always, it's a lot of internal issues, in a sense of, do I really have the nerve to do that? Do I really have do I really have the enthusiasm, the energy, the initiative to do that, and so on? Or or sometimes that's really not a good idea. You think it's a good idea because you've got in your mind, you've got this whole set of things that you're imagining, but those things are not realistic in the world, and it's just not, that isn't a good way to do it, and pick a different direction. But in any case, I'm just seeing a few comments here. Oh boy, there's a question about central banks. That's an interesting question. Lots of people commenting that they came from Lex Fridman's podcast. Good for Lex. He's a great interviewer. I've done lots of interviews with lots of people, and some of them I feel like I'm saying really interesting things, and others I'm like, if I was listening to this, I would be falling asleep. With Lex, he's really good at getting sort of the best stuff out of people, including perhaps me. Let's see, there's comments here. Let me just cover these and then I should get going. Let's see, there's comments from Fabry here about partnering with educators on YouTube to produce content that's interesting, that could show people Yeah, well, this is a comment about showing people that just because you don't know how to do your math exercises really well doesn't mean you can't make great contributions to STEM kinds of subjects. Yeah, I mean, look, I'm a sort of an example of that. When I was a kid, age 9, 10 years old or something, I was like, I don't like math. I'm not very good at it. Other people get much better marks in their, grades in their exercises than I do. I'm pretty crummy at math, but I was really interested in physics. And so I kind of like, I've got to solve this math problem. And so then a little while later, I realized, actually, there's a way to do this. Use computers to do it. So I don't have to do the parts of the math that I find boring and not terribly good at. And so, it's one of these, look, there is a solution, so to speak. And you can get to it. But I think as a practical matter, I hope that, for example, these live streams, and I'd be certainly very interested in people's suggestions about. I think we're chopping up these live streams into podcasts about particular topics. I mean, as you realize, these live streams are 100% off the cuff, and so I'm. But I think, and they're not sort of organized to be about particular topics, but I think we're chopping them up into particular topics, and hopefully they will provide some content that is useful to people in sort of understanding sort of STEM kinds of things, and I hope with decent explanations. I mean, I should say that the things I talk about here, for what it's worth, some fraction of them you could sort of find if you read a bunch of textbooks. Some fraction, I know perfectly well that these are completely not well known and not well understood things that I happen to, for one reason or another, because I've actually studied the science of it myself, or because I know people involved in that area or whatever, I happen to know. And one of the things that I suppose is I don't know whether it's good strategy or bad strategy, but I don't really make a distinction between those things. I'm just sort of saying things like, people know X, Y, Z. It's like, I know that because I know the person who is the leader in that field, who figured that out last year, so to speak. I don't really make a distinction between that and I learned that 50 years ago from some textbook type thing. I suppose that so that's kind of my, I don't think it really matters if the goal is to understand. It doesn't really matter whether I learned that as a very special thing that only I know, or that that's something that's fairly well known. That's kind of a different issue. What I'm trying to do is to explain things, and I have to tell you that for whatever good it may do for other people, these live streams have been great for me, because I am really sure that I have become a better explainer of things through spending this time explaining stuff on these live streams. And I noticed we just had our annual technology conference, and I always do Q&As and things at annual technology conference, and they're spaced a year apart. And I realized I am better at doing these Q&As than I was a year ago. And the reason is because I've been doing these live streams. So that's a thank you to people who've been participating in these. I'm just going to look at one more comment here about reaching people. Okay, there's a specific list of science YouTube channels. I know a few of the people involved in these, not others. Great. Hopefully the team can write down this list and take that suggestion. Okay, good. There's some great great questions saved up for next week. So please tune in again. What's the right word for a live stream? It's not tune in. Tune in is adjust the variable capacitor on your transistor radio or something. I don't know what the right term is. Connect again next week. Look forward to hearing from you all. Thanks for being here. Bye for now. Oh, I'm being told join us is the right terminology. Okay. All right. So bye for now. Please join us again next week.